Is my screen visible? Can any one of you just confirm in the chat box? Okay, thank you. So I guess we are ready to start. Uh, hello, my name is Riddhiman Bhattacharya, and I'm one of the TAs for the course Optical Fiber Sensors, taken by Professor Balaji sir, Balaji Srinivasan from IIT Madras. And I am I'm a PhD student. I enrolled in IIT Delhi. I'm in my first year, in second semester, and I'm a Prime Minister's Research Fellow. So I'll be taking the doubt clearing session. We will be solving some doubts, and I enhance that. Yes, I also enhance that you guys solve it simultaneously. And if you guys have any doubt in any steps, kindly unmute yourself and ask, or you can also ask in the chat box. And while attempting the questions, kindly you guys also participate in giving the answers in the chat box. Is it fine? Can I start? Okay, seems good. So the first question. Uh, which of the following are the key benefits of using the optical fiber sensors? As the following options are all given, it's immune to EMI, namely the electromagnetic interference, the sub-wavelength precision, low attenuation, easy availability of components, or all of the above. Uh, I've also mentioned the timestamp, the answer to the question in the timestamp of the lectures in session week one, from where I have took the questions and answers are also discussed by the professor. You guys, I will be allotting 2 minutes, so you guys could write give the options in the chat box, which one is the correct one. After that, I will discuss it. So kindly 2 minutes only. Okay, option four, easy availability of the components you are telling Shailendra, right? So according to the question, yeah, option five. Yeah. So as discussed by the professor, the question, the benefits are it's like in optical fiber sensors, it's like immune to the EMI and the sub-wavelength precision also it's correct. The low attenuation is also the correct one, and the availability of components in optical fiber sensors is far more easier compared to the electronic sensors. So the right option is all of the above. The next question is the Mach-Zehnder interferometer is typically used in what type of modulated sensors? The options are wavelength, polarization, amplitude, and phase. So the MZI interferometer, which Sir had discussed, so it's basically which operating on which type of principle, like it's modulating the wavelength or the polarization or the amplitude or the phase. Yes, phase is the correct one. If any one of you are having any doubts and unable to understand, kindly unmute or like you can ask in the chat box also. So the next question is, what is the relation of the slope of the launched power in the fiber, denoted as A? I've denoted the slope of that launched power in the fiber as A, and the backscattered fiber, which is denoted as B, in a graph where the graph where the graph is actually power versus distance in the optical fiber. You guys can uh, think a while and write the answer in the chat box also. It's discussed in the second lecture of overview of the distributed sensors. Any one of you could figure out the answer to this question? The relation of the slope of the launched power in the fiber, like so. Uh, as it has been discussed, and mainly the launched power will be like this only. This is slow phase. Okay. So, but the backscattered fiber, the slope of the backscattered fiber will be twice. It will be twice the slope of A. So, because when the backscattered fiber, the signals are coming after a round trip, losses are getting doubled, due to which the slope is also being doubled. So the answer, as we can see from here, the slope of B is greater than the slope of A. Okay, does anyone have any doubt in this question? You can ask in the chat box or unmute yourself also. Okay, so we can move on to the next question, right? So it's a pretty easy question for all of you guys, I guess. The electric field of an electromagnetic wave is represented as A subscript x E naught e to the power j omega t minus beta z. So the frequency in this equation is represented by which factor? E naught, A subscript x, beta, or omega? Yes, option 4 will be the correct one. The next question is similar to the previous one, just the identifying quantity has been deferred. The phase in the above expression is determined by which quantity? E naught, AX, beta, or omega? Okay. Yes. The third option is the right, correct one, the beta. Here, AX being the amplitude and E naught being the initial E field, whereas beta is the phase and this being the frequency. So, the next question is a picturative study question. So, we can see here a source is being attached to a detector via which perturbation are being done. Okay, for fiber sensing. Similarly, in figure B, we can see that the source and the detector are on the same side, like respective to the figure A, that the source and detector are on the opposite side to each other. So, the correct statement on this typical optical fiber sensing configuration as follows: that figure A. Just a sec, let me admit the participants. So figure A is the preferred sensing configuration because it detects more backward light. Figure B is the preferred sensing configuration because it detects lesser backward light. Both the configurations, figure A and figure B, are good for sensing because forward and backward scattering are same, whereas both configurations, figure A and figure B, are good for sensing because the backward light is the same. Yes. So second option, mainly this one is better because yeah, when the detector and source are in opposite direction to each other, it gets detected by more background light, which is an inefficient way of sensing because most scattering will be there and it will not, like for nanoparticles or or minute refractive index changes, it will also be inefficient. But in the second one, when source and detector are on the same side, it will be more efficient because background light will be less. So option 2 will be the correct one. The backscattered power is dashed to the pulse width, like how the backscattered power and the pulse width are related. Is it inversely proportional, or square times proportional, or square times inversely proportional? So Yogesh is telling option 2 proportional. Let's wait for 1 minute for others also to solve. Square times inversely proportional. Yes, Narendra is telling option 1 inversely proportional. So guys, like think it like this way. When the pulse width which we are talking about, like suppose this is the pulse width and this is the line width, or we can say the pulse width, okay? And the backscattered power, as we have seen the slope here, power, it's twice, 2 times the delivered power, okay? And mainly this thing is applicable in OTDR. OTDR stands for optical. So when the backscattered lights are coming, the relay backscattered lights mainly provide the fiber sensing. So when backscattered power will always be proportional to the pulse width. So it goes for option two because as it has also been discussed in that timestamp which I have shown here, the backscattered power will always be proportional to the pulse width which we are sending. If it is n, then the backscattered power 10 times pulse width. Okay. So the next question is, which is not a distributed sensing mechanism? The Raman OTDR, the Belong OTDA, the fiber Bragg ratings, or the phase OTDR. Okay, shall I be some option three? Let's wait for a minute for others also to opt it out. As we know in distributed sensing mechanisms, we have uh, two divided systems like the true distributed sensing mechanisms and the OTDRs. So the OTDR is like in FBG. So what is the difference between the FBG part and the rest OTDR and OTDA parts? In FBGA, we are just sensing at a particular region. So if anything changes around other parts, we will not be able to detect it. Only we will be detecting this part only. But in OTDRs, it's OTDRs are uniformly spread. The sensing regions is uniformly spread, or as termed as uh, two distributed sensing mechanisms. So for this part, the not distributed sensing mechanism will be the fiber Bragg grating one. Okay. Does anyone is having any doubt regarding this? Okay, we are moving on to the next one then. So it's a numerical based one. So a continuous 40-kilometer long optical fiber. So let's solve it together only. You can do it simultaneously and we will finally match the answers. Okay. So a continuous 40-kilometer long optical fiber link has a loss of 0.4 dB per kilometer. So please answer the following with one decimal accuracy. Dash dBm is the minimum optical power level that must be launched into the fiber to maintain an optical power level of 2 microwatt at the receiving end. So, and the input power and the power is given as 2 microwatt. So as dB is given, we have to convert the microwatt into dB, which will be approximately minus 26.9 dBm. Okay, so we are getting it right. This one. Are you guys continuing simultaneously too? So after this, we have to find the minimum optical power. So what's the formula for that? Input power minus loss due to and equals to the output power. So input power we have to find. It's the question. So the answer which I am getting is 10.9 minus 10.9. Uh, have you also got this one? Kindly follow the steps as the next question is also uh, following the similar pattern only. So the next one you will be able to solve it individually. So what we are getting, the attenuation for is zero point 0.4 dB per kilometer. So as we are receiving 40 kilometer here, so then the 40 in the 40 kilometer we are receiving here. So for the full 40 kilometer, how much is the attenuation? Is 16 dB, right? And the power is 2 microwatts, but in microwatts we have to convert in dB. So for by the conversion we are getting it minus 26.9 dB. So and here the answer to the question is here. What is the minimum optical power level that must be launched? That is the input power. The input power minus the loss due to attenuation should be the output power. Okay. So as we are giving input through one end, suppose this is the optical fiber, we are giving input as the ray propagates light, attenuation occurs, which gives us the output power. If we so if we want to receive this output power, input power will be minus of the attenuation. Similar, this part only I have written here, and for the input power, I founded out this one. So the answer will be minus 10.9. Okay, just follow this test because the next part is also this one. So I will enhance all you guys to solve it individually. Is it okay? Like, should I keep the previous slide on so that you get a reference by noting down the values? The values are same only, only the loss is different. There was zero point 0.4, here we have zero point 0.6. Everything are same. So are you guys solving it? 0.6 is given here. The whole length of the fiber is 40 kilometers. Then what is the total attenuation? Can any of you guys tell what is the total attenuation in chat box? Okay, the answer you are telling us input power you're telling minus 2.9, right? Okay, let's see, we will solve it. So 0.6 into 40, 24 dB, and the input power will be, okay, you guessed 24 dB attenuation. And the input power minus this 24 will give us this 2 microwatt. We'll convert it, so we'll get minus 26.9, right? So input power will be minus 26.9 plus 24 minus 2.9. Yes, Sri Ram Ganesh and Shailendra, you guys are right. It's minus 2.9. Okay. Uh, so everybody got the answer. Can we move on to the next question? If anyone is not having any doubts regarding this. Okay. The next are generally easier comparative to the previous ones, the basics and photonics. So why does the sky appears blue? The options are reflection of seawater, light scattering in atmosphere, other other colors are absorbed in the atmosphere, and the emission from atmosphere. So can any one of you guys just try it out? Option two, Challenger is telling option two. This phenomenon is mainly occurring due to the Rayleigh scattering. You guys surely will know it. Rayleigh scattering. And the Indian scientist C.V. Raman, who got the Nobel Prize due to his Raman effect, also like he was just observing this oceans while sitting on the sea beach when he saw that why the color of the sky appears blue and why the water droplets are also appearing blue. So mainly due to this only he gradually moved on to win his Nobel Prize with his idea of the Raman effect. So yes, the correct answer is light scattering in the atmosphere. Yes, Sri Ram Ganesh. The option two is right. The next question is it's a multiple options, the multiple correct answer question. So more than one option is correct in this four. Okay, so opt it like that way. When the light propagates in a medium, physical processes that it undergoes include. Suppose when a light is moving in a medium of n suppose. So the physical processes which it undergoes, what will be those physical processes among these four? Suppose light is going through a medium of water, 1.5, or oil. What characteristics will be followed here? Can anyone try it out among these four? Will absorption occur? Like when the light falls on some material, does light gets absorbed or not? Can any one of you guys try it out and write in the chat box? Yes, it does get absorbed. When light is fall, one Anirudh, Shailendra option three, I think. So Shailendra is saying option three and Anirudh is telling one. Okay, you see, yes, absorption will be taking place obviously, and scattering. When a light is coming on a surface, does light get scattered on surface of scattering, absorption, dispersion, and scatter? Okay. Yeah, so when light is falling on a medium, does it get scattered or not? Yes, it gets scattered, due to which we can see the color of the sky blue as previous discussed in the previous question. Dispersion. Does dispersion occurs when a circle, when a sphere wall is kept and light is being passed, or suppose an aperture is kept and light is being passed. So, according to the particle theory of light, uh, uh, according to Einstein, which believed that light is a particle, it should be like this, right? But Fresnel and Huygens, they resolved it out that beyond this part also, light gets light gets spread. So why does it get spread? Suppose if it's a particle, suppose a dot is coming on the screen. So here is it is illuminated. This part will be dark, but it has been seen that it's getting gradually done. Suppose this is the intensity at that part, and so like this, the intensity is getting lower. So it's not a distinct shift from from brightness to darkness, but a gradual shift, which explains the phenomenon that at these edges also light gets spreaded, which is the main fact of dispersion. So yes, dispersion also occurs. And due to dispersion, yes, interference occurs. But when light propagates in a medium, interference does not occur there. Interference occurs in constructive interference or destructive interference. But here, when the light propagates in a medium, the physical processes which it undergoes will be only absorption, dispersion, and scattering. Interference is seen only on screen. If we are like if the Young's double slit experiment, if we are doing, okay, if we are staying, then only like this we will be receiving the interference, not while propagating through a medium. Okay, so we are moving on to the next part. The It's a pretty simple one for everyone here, I guess. The visible spectrum extends from what nanometer to what nanometer? Kindly everyone, may write 400 to 700. It's the span for this is 400 to 700. These are all your assignment zero questions, so I'm discussing it as it's non-marked. The previous questions were to give a pathway for the assignment one. Next week, I'll also discuss according to those week two lectures upon which the optical sources and optical receivers one and two are discussed. So, for a glass prism illuminated with white light, which color will bend more? Given the refractive index decreases with wavelength. Bend more, bend more is yes, correct. Red one will be bending least, and the blue one will be bending the most among these the options here. Sorry. So let's assume that we are inside water and a green laser beam is flashed at us into the water. What color will we see from inside the water? The refractive index of water is given 1.33. So the main point is green laser beam is given here, and we are seeing it from inside a denser medium like air and water. Yes, so Swatika has given its green. Okay. So white screen, can you just write it down like short in the chat box? Why will it be green or unmute, whatever is comfortable to you? As we all know that the mainly the color is dependent upon frequency, and the frequency uh, doesn't doesn't change upon change so the frequency doesn't change upon the change in medium. The whereas the wavelength changes. So as the wave when the so wavelength changes, but here we are seeing the color. So as the color is remaining unchanged, so green will be the correct one. The critical angle for TIR, total internal reflection of the air-water interface, is N is given this. So the formula for this is sine inverse 1 by n, right? Because as it's going from air to water, air stands here for the 1 and n is the 1.33. So the yes, 48.75 is correct. Question 16. The red light of 650 nanometer is traveling from air to glass medium. Consider the refractive index of glass is 1.5. Find the wavelength and frequency of the light beam in the glass. Can you guys just talk it out and let me know the answer in the chat box of this question, which was one of the questions in your assignment zero also, I guess. Can you guys tell the wavelength? What will be coming? Will it be for 433.3 nanometer or 333.3 nanometer? It will be 433. So automatically option C and D are incorrect. So the frequency of the light beam. Swatika has told that option 1 is the correct one. Let's see. The frequency. So frequency will be given here by C by lambda. So 3 into 10 to the power 5, 15 into 10 to the power minus 9, 14, 3 by 2 into this. Option 1 will be the correct one. So as many of you were not in the, so this one was the last question for today. As many of you were not in the first half of this session, these were one of the pretty easy ones from assignment zero. Um, this question was not answered by anyone. Is anyone having any doubt on this one? Like how it's coming? What is the relation of the slope of the launched fiber in the launched power in the fiber, denoted as A, and backscattered fiber denoted as B in the graph of power versus distance in optical fiber? Did you guys understood like how it's coming? As I've also mentioned the timestamp, you can just once refer to that part of the video. So as I already mentioned, then the launched power here is the A part and the backscattered fiber is the B part. Okay. So when why the slope of this B is 2 times of A? Because when the B is coming, the losses are getting doubled. Well, in the backtrack or not backtrack, it will be the total path length. In the total path length, it will be constituting both the losses of A plus B. So it will be 2 times of A. So the slope of B is always greater than the slope of A. As it has been mentioned by Sir also, when we are getting the backscattered light here, and there is some PD or the noise level, which is being noise level which we receive. But as so kindly show question number one. Okay. Just let me finish this one. Now question three, then I'm showing the one and two. Okay. So as this is a single frequency, so the noise level is here, but we want the maximum distance, right? As in the discussion, it was shown that the dynamic range should be as high as possible, right? So this thing we have to lower it. So how it is being lowered? When it is a single frequency, but when we are averaging out a number of frequencies, this noise level gets reduced here, as it has been shown in that timestamp part. Then the dynamic range part also gets increased, due to which it gets more, the part where the sensing is done increases, so it can sense more acute results also. Okay. This question one and two were pretty straightforward. It was question one gives us the key benefits of using the optical fiber sensors. Uh, as all these are correct to the beneficiaries of the optical fiber sensors, we are also seeing this. I'm sorry, I just got disconnected due to network issue. Uh, So I was there that as all of them are EMI, the sub-wavelength precision, low attenuation, all are equal. So sub-wavelength precision also comes in the plasmonics part, which is a different sector of optics. Low attenuation also comes in sensors. Easy availability is there and immune to EMI, which plays a major role compared to those in the electronic sensors. And the Alexander interferometer was the second one, which is typically used as what type of sensor? As we all know that it inverts the phases, and so it's a phase modulated sensor. Okay, these are pretty straightforward. This was a question from the main part. The source and detector positioning. The source and detector positioning, as backscattering is more here in this part, as they are opposite to each other. So this is less efficient. But when we are keeping the detector on the same side as the source, it detects lesser background light, right? So due to this, the figure B is the preferred sensing configuration. And backscattered lab question 7 was the backscattered power is how it is related, or how the relation is there between backscattered power and the pulse width. Uh, Two, three of them got the answer incorrect. One was saying that inversely proportional and one was saying square times inversely proportional. But it will be proportional. I have also mentioned the timestamp where Sir has mentioned how it's coming. The 19.31 seconds there we can see that. Then, as I have also mentioned here, the pulse width will be and pulse width line width of the signal in OTDR, optical time domain reflectometry, will be the back it's proportional to the pulse width. And so for the eighth question, which is not distributed sensing mechanism, the fiber bracketing, as we discussed, that it is particular to those where the gratings are done. If we anonymously take any part and sense that and something is occurring in that part, suppose temperature is being varied, we can't sense that part because the FBG is only like concentric to the part where we have done anomalous gratings and we are sensing in that part only. But in distributed sensing, so the true distributed sensing, we see the uniformly. So in OTDRs, OTDA, OTDR phase, all are uniformly distributed. So any changes in refractive index or any change in anything will be detected instantaneously by these sensors. So it's mainly the distributed sensing mechanism. And then this question 9 to we have solved. So all of you have solved it simultaneously only with me. So, any of you guys are having any doubt regarding the videos which sir posted? Today's session was basically on the week zero assignment and an overview over the week one videos, questions from which I've made to give you an overview like how the assignments are being solved. In the next week, same time, I will be giving an overview with more questions on week two lectures, the optical sensors, the optical receivers one and two. I'll be making questions from those so we can do it simultaneously and get a more in-depth knowledge about those. So if you guys are having any doubts, you can ask me out in the chat box or in by unmuting your mic. Sorry. So, is everyone here a BTech student or MTech and PhDs are also here in the current meet? How many of you are BTech? Can you raise your hands or write in the chat box if possible? So, how many of you guys are BTech students or MTech or PhDs? Okay, so Sriram Ganesh, Yogesh, and Anirudh are BTech, MTech, or PhD? Which ones?
A PhD, sir. Doing PhD.
BTech, okay, BTech. Okay, 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 okay. So your current research is also maybe on optical fibers only, I guess. Today's session was a comparatively very easier one, but the next session will be more focused on the questions from the questions from the videos only. So it will be more interesting and more engaging for both sides. As we move on to further lectures, we will be receiving more in-depth knowledge, and so the questions will be more precise. And I will also increase the number of questions to take a session quite a bit longer. So if both sides interact just as today or increase, it will be a more beneficial one. So mostly a PhDs only. Okay. Okay, so thank you guys for today. Next week, kindly join at the mentioned time at 7 p.m. On Tuesday. We will just move on further with the week two's discussions. And kindly, if you have any doubts regarding the week two or one, anything, you can just drop a text in the discussion forum in Google Groups, or you can ask in this meet only next Tuesday. Thank you, Shannon. Thank you, everyone. Okay, thank you. Okay. So you guys can leave as we have wrapped up the meeting. We can.